Massive machines, non-stop prep lines, and food built for speed. This is how America's favorite chains keep millions fed every day. From shaping donuts at industrial scale to assembling sandwiches in seconds, Dunkin, Subway, and Chipotle all rely on powerful systems behind the scenes. In this video, we take you inside the factories and kitchens where your favorite fast food really comes to life. It all begins long before a Dunkin Donut ever meets a customer's lips. The journey of a factory-made Dunkin Donut starts in massive industrial facilities engineered specifically for high-throughput baking and frying. Unlike the fresh, hand-prepared donuts in local bakeries, the factory-produced donuts that supply regional distribution centers or large retail outlets are the result of a tightly choreographed sequence of automated, mechanized operations, each designed to maximize consistency, food safety, and output volume. The core ingredients of a Dunkin Donut seem simple: wheat flour, sugar, yeast or chemical leavening agents, eggs or egg solids, milk derivatives, oil, and water. But each of these components must meet stringent specifications. The wheat flour is typically sourced from large milling operations and arrives at the factory in bulk pneumatic tankers. Once offloaded into giant silos, it's carefully monitored for protein content, moisture, and particle size. These parameters are crucial as they directly affect gluten development, dough elasticity, and fry stability. The sugar, often in fine granulated form, is similarly delivered in bulk and stored in temperature-controlled hoppers to prevent clumping. The yeast, which may be active dry or instant, is carefully handled to maintain viability. For cake-style donuts, chemical leaveners such as sodium acid pyrophosphate and baking soda replace yeast, requiring exact dosages to control rise, texture, and batter pH. Liquid ingredients like water and milk concentrates are pumped from stainless steel reservoirs through filtered lines. Egg solids, whether powdered or liquid, are introduced via sealed containers to reduce contamination risk. At the heart of the process is the dough preparation system. In a typical yeast-raised donut line, a computerized batching system automatically dispenses pre-weighed quantities of dry and wet ingredients into a horizontal spiral mixer, usually a high-capacity unit capable of mixing several hundred pounds per batch. This mixer blends the ingredients through a timed, multi-speed cycle, a slow initial mix to hydrate the flour, followed by a high-speed kneading phase to develop the dough's structure. Temperature probes ensure the dough reaches the optimal final mix temperature, often around 78 to 82 degrees. Any deviation can alter fermentation speed and finished product quality. Once mixed, the dough is transferred, either manually in smaller setups or via automated dough elevators in large-scale operations, to intermediate proofing cabinets. These are large chambers that maintain a warm, humid environment, typically around 90 degrees Celsius, with 85% humidity. The dough rests here for 30 to 45 minutes, allowing initial yeast fermentation to begin. This resting period improves extensibility and relaxes the dough for sheeting. From the proofing cabinet, the dough moves to the sheeting line. Here, massive rollers flatten the dough to a precise thickness, often controlled by laser-guided sensors. A conveyor belt feeds the dough through a series of increasingly fine rollers, each pressing it thinner until it reaches the exact gauge required for donut formation. Dusting flour is automatically sprinkled to prevent sticking, and scrap management systems collect unused dough trimmings to be reprocessed in future batches. Next, the formed dough sheet moves to the rotary cutter station. This is where the signature donut shapes come to life. Custom-designed rotary dies stamp out rings, holes, or specialty shapes like filled bars or seasonal themes. Each cutter is precision machined to minimize dough stress, ensuring even fry results. A vacuum system gently lifts and removes cut donuts from the scrap dough matrix, depositing them onto another conveyor in perfect alignment. These unbaked, shaped donuts are then transferred to the final proofer, a massive multi-tiered system that can resemble a vertical carousel. Moving slowly through this enclosed environment, the donuts are proofed for anywhere from 35 to 60 minutes, depending on product type and yeast activity. This is a critical phase. The dough expands, air cells develop, and the signature light texture of a yeast donut forms. Relative humidity and temperature are tightly regulated to promote even rising. Once proofed, the donuts enter the fryer. This is one of the most visually captivating moments in the factory. Rows upon rows of pale, risen dough transforming into golden brown perfection. Industrial donut fryers are long, shallow troughs filled with high-stability frying oil, typically a blend of soybean or palm oil, designed to withstand high temperatures without breaking down. The donuts enter via an automated conveyor that gently lowers them onto the surface of the hot oil, held between 350 to 375 degrees. Floating racks or submerged mesh baskets keep the donuts evenly spaced and ensure uniform frying on both sides. The donuts are flipped halfway through using automated paddles or turning bars, so each side receives equal exposure. Fry time is typically 90 to 120 seconds per side for yeast-raised varieties. Throughout the fryer, oil filtration and replenishment systems remove debris and maintain oil quality, critical for flavor, texture, and food safety. After frying, the donuts move onto a draining belt where excess oil is wicked away using absorbent conveyor surfaces or air knives. From there, they transfer directly to a cooling tunnel, an enclosed, climate-controlled conveyor that gently brings the donuts down to ambient temperature. This cooling phase, usually lasting 8 to 12 minutes, stabilizes the structure and prevents condensation before glazing or filling. Now comes one of the most iconic steps: glazing. The donuts pass beneath a cascading curtain of warm glaze, typically made of powdered sugar, water, and stabilizers like corn syrup or mono and diglycerides to ensure sheen and viscosity. The glaze is held at precise temperatures, around 105-115 degrees Fahrenheit, to allow smooth coating without excessive dripping. Any glaze runoff is collected, filtered, and reused within quality limits. For filled donuts, a separate line handles injection. This is a precise, high-speed process where each donut is clamped and filled through nozzles that inject jelly, cream, custard, or other fillings. Volumetric pumps control exact fill amounts, typically between 15 to 25 grams per donut, to ensure uniformity. The timing of this step depends on whether the donut is glazed before or after filling, a decision made based on the type of coating or desired product appearance. Topped donuts, such as Boston cream or chocolate frosted, pass through enrobing units or individual depositor stations. These machines spread or pipe icing onto the surface, using rotating drums or mechanical arms to achieve even distribution. Sprinkles, nuts, or other toppings may be applied via shaker systems or robotic garnishing heads, with vacuum sensors ensuring no foreign objects are introduced. Once coated, the donuts continue on conveyors to the packaging area. Here, an optical vision system inspects each unit for shape, color, topping placement, and fill integrity. Defective products are automatically rejected and diverted for analysis or disposal. The acceptable donuts proceed into robotic tray loaders or auto packing machines. For bulk shipments, donuts may be arranged in plastic trays stacked into crates. For retail packs, form-fill seal systems wrap donuts in individual or multi-unit blister packs using heat-sealed film. Each packaged unit receives a date code and product identifier via inkjet printer or laser etching. Metal detectors and X-ray scanners stand guard just before final packaging to catch any foreign materials, from metal fragments to hard plastics. At this point, the product has passed through over a dozen safety checks, far more rigorous than what a local bakery could feasibly achieve. Before leaving the factory, pallets of donuts are weighed, logged, and tagged with RFID labels for inventory tracking. They're stored in temperature-controlled staging areas until trucks arrive. Distribution fleets, often operated by third-party logistics firms, are designed to transport the donuts quickly to regional warehouses or direct-to-store delivery networks. Because many factory-made donuts are frozen for extended shelf life, refrigerated trucks or freezer compartments maintain ideal storage conditions throughout transit. Once at a distribution center or store, the donuts are thawed if necessary and either resold in packaged form or used to stock fresh counters in Dunkin outlets. Some outlets may perform final finishing touches, like adding fresh glaze, sugar dusting, or customized toppings. But the bulk of the preparation has already occurred at the factory, where industrial consistency reigns supreme. Before a Subway sandwich ever reaches the customer's hands, its journey begins far from the store counter, in sprawling, high-efficiency food manufacturing plants that are responsible for producing the standardized components that make up the brand's globally recognized product. While each Subway location assembles its sandwiches fresh to order, the bulk of the ingredients, the breads, meats, cheeses, sauces, and even vegetables, are processed, prepared, and packaged in industrial facilities built for consistency, volume, and food safety. These components are the result of complex, multi-step production lines designed to meet Subway's stringent specifications across every country they operate in. The foundation of any Subway sandwich is the bread. While baked in store for aroma and freshness, the bread dough itself is manufactured at specialized commercial baking facilities. These plants begin by sourcing massive quantities of high-gluten wheat flour, usually delivered in pneumatic tankers and stored in tall, stainless steel silos. The flour is tested for protein content, ash level, and moisture to ensure it falls within tight tolerances required for consistent dough performance and volume expansion. Once quality is confirmed, the flour moves via auger or vacuum transfer to automated mixing systems. Each variety of bread, Italian, honey oat, hearty multigrain, and so on, has its own formula, managed by a PLC-controlled batching system. Water, sugar, salt, yeast, dough conditioners, and enrichments like wheat germ or oats are dispensed in precise quantities and sent into high-capacity spiral mixers. These mixers, with capacities reaching up to 1,000 pounds per batch, perform a sequence of low-speed and high-speed kneading to develop the gluten network necessary for Subway's springy, chewy bread texture. Temperature-controlled water and chilled mixing bowls help maintain the dough temperature, typically around 78 degrees Celsius, essential for proper fermentation. After mixing, the dough is unloaded onto transfer belts and sent into a first-stage resting tunnel or intermediate proofer. Here, the dough rests in a humid, warm environment to allow the yeast to activate and create carbon dioxide, giving the dough extensibility before shaping. Next, the dough is portioned using volumetric dividers that slice the mass into uniform weights. These pieces then pass through rounding and molding machines that elongate them into the familiar Subway sandwich roll shape. Automated flour dusters and non-stick belts ensure smooth passage through the shaping process. For breads with toppings like oats or cheese, the dough passes under a rolling applicator or static sprinkler before entering the next proofing stage. The proofing phase is critical. Dough pieces are placed onto pans and loaded into an industrial proofer, a large, climate-controlled chamber with tiered racks or chain-driven carriers. Inside, the bread rises for 45 to 60 minutes at around 90 degrees Celsius with high humidity. Dough height, elasticity, and fermentation rate are monitored using sensors or inline imaging to to guarantee uniform rise. Once proofed, the dough pans move into the par baking ovens. These are tunnel or rack ovens heated to approximately 420 deg. The bread bakes for about 8 to 10 minutes, enough to set the structure and crust, while preserving enough internal moisture so it can be finished baking in store. After baking, the loaves are cooled in ambient air tunnels before being packaged. Packaging is a delicate process. The cooled loaves are inserted into specially ventilated film or bulk freezer trays. Modified atmosphere packaging may be used to extend shelf life and prevent freezer burn. All packaging is date-coded, labeled with batch tracking, and sent through metal detectors or X-ray systems. Then the bread is quickly frozen in blast freezers that bring core temperatures below zero in under 90 minutes, preserving quality for shipment. While the bread is handled this way, meat and poultry ingredients follow a parallel but very different industrial route. Subway's deli-style meats, turkey breast, ham, roast beef, and chicken strips are cooked, sliced, or formed in specialized meat processing plants. These facilities receive USDA-inspected raw proteins that are boned, trimmed, and cleaned under strict sanitary guidelines. The raw meats are portioned, tumbled, and marinated with Subway's proprietary brine formulas, which often include salt, phosphates, sugar, and flavorings. In the case of chicken strips or patties, the meat may be fully cooked in steam ovens or grill presses, then flash frozen to lock in moisture. Roast beef and turkey, on the other hand, are typically cooked in steam ovens or combi ovens that simulate traditional roasting while maintaining high throughput. Once cooked, the meats are cooled using spiral chillers or glycol plate systems, then sliced on high-speed rotary slicers for uniform thickness. These slices are stacked and portioned by weight using automated weighing machines, then sealed in vacuum pouches or controlled atmosphere trays. Each portion is sealed with batch coating and passed through inspection systems before being packed into cartons and frozen for distribution. Cheese slices, Swiss, American, provolone, and pepper jack are produced using high-speed forming and slicing systems. Cheese blocks are first melted down, then reformed into large sheets which pass through slicing blades and portion conveyors. Anti-stick sheets are often placed between slices, and stackers organize the cheese into count-specific bundles, each packaged under vacuum or gas-flushed atmospheres to preserve shelf life and prevent molding. Vegetables such as lettuce, tomatoes, cucumbers, onions, and green peppers are not grown in factories, but they do undergo industrial preparation before arriving at each store. Lettuce, for example, is harvested, washed with chlorinated or ozonated water, and shredded in high-speed slices. Tomatoes are cleaned, visually inspected, and machine sliced before being layered between food-safe pads that prevent bruising during shipping. Onions are peeled, sliced, and packaged in gas-flushed bags to reduce spoilage and preserve freshness. All vegetables are packed in refrigerated, ready-to-use formats and delivered through cold chain logistics to ensure they remain crisp and safe for consumption. Subway's specifications for produce are among the most rigorous in the QSR industry, often requiring vendors to perform multiple microbial tests before product release. Sauces, ranch, Chipotle Southwest, mayonnaise, mustard, sweet onion, and many others are made in liquid processing plants that function much like beverage or dairy factories. These facilities handle emulsion preparation in large mixing tanks fitted with high-shear homogenizers. Ingredients like oils, water, spices, thickeners, and preservatives are blended under vacuum to ensure air-free, stable emulsions. The sauces are then pumped into sterile filling machines that dispense measured volumes into squeeze bottles, bulk pouches, or portion cups. Heat sealing, tamper-evident caps, and nitrogen flushing preserve shelf life. Every component, from bread to sauce, is designed with logistics and final assembly in mind. Once all the parts are complete, They're loaded onto pallets, sorted into refrigerated and frozen shipments, and transported to Subway's distribution centers. From there, truck routes are carefully scheduled to ensure timely delivery to thousands of store locations. All products are scanned, tracked, and recorded during shipment, ensuring cold chain integrity and traceability from plant to sandwich counter. Inside the store, the staff becomes the final assembly line. Each morning, the frozen bread dough is thawed and given a second proof before finishing its bake in the store's convection ovens. Meats are defrosted and held in refrigerated bins, vegetables are placed into prep trays, and sauces are opened and loaded into squeeze bottles. Sandwich artists follow precise build sheets and portioning guides to ensure a consistent experience for the customer. Even at the store level, there are echoes of the factory's precision. How many ounces of lettuce per 6-inch sandwich? How many slices of meat? What angle to cut the bread? It all comes back to what was engineered upstream. Without the highly standardized processes in the manufacturing plants, the in-store experience wouldn't feel as predictable and familiar across the world. The industrial journey of a Chipotle meal begins with ingredient sourcing. Chipotle is known for its emphasis on food with integrity, which means that much of the upstream processing is tightly controlled, even before the factories get involved. The chain sources meats that are often antibiotic-free, pasture-raised, or sustainably farmed. These meats arrive at centralized processing plants, some Chipotle-operated, others contracted to third-party co-packers, with exacting specifications. Take chicken, for instance, one of Chipotle's most popular proteins. Whole chicken breasts and thighs are delivered from certified suppliers in refrigerated transport and immediately placed into cold storage bays at the processing facility. These facilities are equipped with advanced sanitation systems, including antimicrobial entry zones and HEPA-filtered air circulation to maintain a sterile environment. The chicken is deboned, trimmed of excess fat, and portioned into standardized sizes using automated cutters. Optical sorters with high-speed cameras and laser detection systems inspect each piece for defects, bone fragments, or inconsistencies. After cutting, the chicken moves into industrial tumblers or vacuum mixers where it is marinated. The marinade consists of oil, spices, garlic, citrus juices, and chipotle pepper, all pre-mixed in large blending tanks. These tumblers are designed to evenly coat the chicken while tenderizing it, using a slow rotational motion that lasts anywhere from 20 minutes to several hours, depending on the specific formulation. The chicken is then sealed into vacuum-packed pouches or bulk containers and flash-chilled. In many cases, the chicken is shipped raw to Chipotle locations, where it is grilled fresh daily. However, in higher volume markets or during peak operational periods, some portions may be pre-cooked using commercial-grade combi ovens or grill presses inside regional commissaries. These ovens are steam-injected and heat-distributed, ensuring that the chicken reaches internal temperatures of 165 degrees without losing moisture. After cooking, the chicken is cooled through rapid chill spiral systems that reduce the temperature below 40 degrees in less than 90 minutes, in compliance with USDA food safety standards. Now let's move to beef, specifically the barbacoa and steak options. These are handled in meat facilities equipped to manage tougher cuts like shoulder clod or round for barbacoa, and sirloin or top butt for steak. The barbacoa beef is typically seasoned, seared, and slow cooked in massive steam kettles or pressurized braising tanks. These tanks operate on programmable logic controllers that maintain precise temperatures and cook times, allowing the meat to tenderize while absorbing the bold, chipotle, and cumin flavors characteristic of the dish. Once fully cooked and shredded by automated paddles, the barbacoa is portioned into pouches and vacuum sealed. It's then rapidly frozen using cryogenic tunnel freezers, often with liquid nitrogen or CO2, to preserve texture and moisture content. Steak, on the other hand, may be seared and sous vided, then chilled and packaged for final grilling in-store, allowing for that signature charred flavor upon finishing. Beans, both black and pinto, are another central component of Chipotle's offerings, and their factory preparation is highly systematic. Dry beans are received in bulk sacks and stored in silo bins, where they undergo cleaning, sorting, and rinsing. Industrial bean cookers, large rotating steam kettles or pressure vessels, hydrate and cook the beans using temperature and pressure sensors to ensure that every batch hits the ideal softness and moisture level. Chipotle's beans are often seasoned with bay leaf, garlic, cumin, and salt, and held in stainless steel jacketed tanks for blending. After cooking, beans are cooled, portioned into food-safe containers or sealed bags, and transported under refrigeration to stores, where they are reheated and seasoned further before serving. Some regional commissaries may do the final seasoning step in-house, using proprietary spice blends and steam kettles to reduce in-store labor. Next up is the rice, a deceptively simple but carefully controlled product. Chipotle's cilantro lime rice, white or brown, begins with high-grade long-grain rice sourced from domestic or South American suppliers. At the processing plant, the rice is rinsed to remove excess starch and then batch cooked in industrial steamers or pressure rice cookers. These machines are equipped with moisture and temperature sensors to maintain the exact texture and doneness that Chipotle requires. Fluffy, but not mushy, firm, but not undercooked. Once cooked, the rice is transferred to large mixing bowls where lime juice, chopped cilantro, and salt are added. Some facilities add a touch of oil for separation and sheen. Pneumatic arms or food-safe agitators mix the rice gently but thoroughly. From there, it is either packaged hot for immediate shipment or chilled using blast chillers and packed cold for later reheating in-store. Salsas, like the mild tomato salsa, corn salsa, and spicy red chili version, are produced in facilities that combine both fresh vegetable processing and sauce manufacturing capabilities. Roma tomatoes, tomatillos, onions, and jalapenos are washed, diced, and de-seeded by high-speed dicers equipped with antimicrobial wash cycles. The chopped ingredients are portioned into blending tanks, where citrus juice, cilantro, salt, and spices are added. These tanks are chilled to preserve freshness during mixing. The salsas are filled into containers using multi-head fillers, which ensure precise weight and avoid overfilling. Each container is lidded, labeled, coded, and passed through X-ray or metal detection systems before being boxed and shipped under refrigeration. Because Chipotle prides itself on using fresh, preservative-free salsas, the cold chain must be rigorously maintained, and shelf life is generally short, often under 7 days. Guacamole is arguably one of Chipotle's most iconic items, and it, too, is partially factory produced to reduce in-store prep time. Avocados are shipped to processing plants where they are ripened in ethylene-controlled ripening rooms. Once they reach optimal softness, they are halved, pitted, and scooped using semi-automated systems. Some facilities still rely on manual scooping to preserve texture and quality. The avocado pulp is then mixed with red onions, cilantro, lime juice, salt, and jalapenos in large mixing vessels outfitted with slow-speed paddle blades to avoid over-pureeing. The finished guacamole is portioned into food service containers and sealed under nitrogen-rich modified atmosphere packaging to prevent oxidation. These are chilled and shipped directly to stores, where they are used within a few days. Even toppings like shredded cheese and lettuce are processed off-site. Cheese blocks, such as Monterey Jack and white cheddar, are shredded using rotary shredders that minimize clumping and deliver consistent length and thickness. The shreds are dusted lightly with starch or cellulose to prevent sticking, and then packaged in gas-flushed bags. Lettuce, typically romaine, is shredded, washed, triple rinsed, and run through centrifugal dryers before being packed in bulk bags with breathable liners. All of these components, once prepared, are transported through a tightly managed distribution network. Refrigerated trucks, monitored with GPS and temperature sensors, deliver ingredients to regional distribution centers or directly to restaurants. There, store teams receive shipments, log temperature compliance, and rotate stock to maintain freshness. From an industrial standpoint, the brilliance of Chipotle's system lies in its hybrid model. It doesn't fully outsource prep, nor does it rely completely on in-store scratch cooking. Instead, it shifts labor-intensive, food safety-sensitive processes like meat marination, slow cooking, salsa preparation, and bean cooking to industrial plants, while retaining finishing touches like grilling, assembling, and seasoning at the store level. This allows the brand to maintain the perception and flavor of real food without the variability or inefficiency of completely decentralized preparation. Behind the scenes, teams of food scientists, process engineers, and quality assurance technicians work constantly to refine this supply chain. They use high-resolution cameras, digital sensors, and real-time tracking to ensure consistency from one end to the other. Batch codes, microbial testing, and predictive analytics help catch problems early, whether it's an out-of-spec chicken marinade or a salsa with an inconsistent heat profile. The core of Coca-Cola's production begins at the local bottling facility. These factories are strategically located around the world to minimize transportation time and maximize freshness. While the Coca-Cola company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and check weighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into six-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remains simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, from syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. To begin understanding how Dr. Pepper is made, we have to step inside one of the massive regional bottling facilities operated by licensed partners. These plants are the heartbeat of the Dr. Pepper supply chain. They don't just bottle soda, they engineer precision, maintain sterility, and manage staggering volumes of ingredients with scientific exactness. Everything begins with water. Although soda is often celebrated for its flavor, more than 85% of the final product is purified water. And not just any water, ultra clean, neutral, flavorless water that forms the foundation of every bottle. This means municipal or groundwater entering the plant must undergo intensive treatment. The first stage of this treatment process uses coarse filtration to remove large particles and suspended solids. Then, the water is passed through activated carbon beds to eliminate chlorine, chloramines, and any volatile organic compounds that could distort the flavor. From there, the process shifts to more advanced techniques. Reverse osmosis membranes, or ultrafiltration units, strip the water of minerals, microbes, and trace contaminants. Ultraviolet light, or ozonation, finishes the process, sterilizing the water and rendering it free of any taste or odor. The water is now ready, perfectly clean, chemically stable, and ready to receive the flavors that define Dr. Pepper. Parallel to this, syrup preparation takes place in a separate, sanitized mixing room. The base flavoring for Dr. Pepper arrives at the plant in concentrated form, pre-blended by the brand's flavor division under tight secrecy. These concentrates are stored in stainless steel containers and handled with care, with operators measuring and metering the required amounts into large batching tanks. In these tanks, often fitted with high shear mixers, agitation paddles, and precision load cells, the base concentrate is combined with purified water, sweeteners, and acid. In the region, the sweetener may be high fructose corn syrup or cane sugar. The acid, usually phosphoric or citric, helps balance the syrup's pH and sharpness. The mixture is stirred and recirculated until it becomes a uniform, homogeneous syrup with exact Brix values, the measure of dissolved solids in a liquid, often used to calibrate sweetness levels. Before it moves forward, the syrup batch undergoes quality assurance checks. Technicians take samples and run tests in on-site labs, analyzing Brix, pH, color, and aroma. Only after it passes these strict controls is the syrup cleared for the next phase, beverage blending. In a process called proportioning, the syrup is metered and blended with purified water in exact ratios, typically around 1 part syrup to 5 parts water. This mixture becomes the flat, uncarbonated Dr. Pepper base. The proportioning system is controlled by flow meters and programmable logic controllers, ensuring that the mix is stable within a tight tolerance band. Every shift, every batch, whether it's in Texas, Ontario, or the Philippines, must deliver the same flavor profile. With the beverage mixed, it's time to add the fizz. Carbonation is one of the most technically critical steps in soda production. The pre-mixed Dr. Pepper is chilled to just above freezing, typically around 35 degrees, to increase its ability to absorb carbon dioxide. CO2 is stored in large tanks on site and is food grade, filtered, and monitored for purity. The cold liquid is forced through a carbonator where fine CO2 bubbles are injected under high pressure through porous diffusers or sintered steel plates. Proper carbonation is both science and art. If done poorly, the soda may foam excessively during bottling or taste flat when opened. The target for Dr. Pepper is usually around 2.5 to 3.0 volumes of CO2, enough to give it its characteristic zing without overwhelming the complexity of its 23 flavor blend. The carbonated product is now pressurized and ready for immediate bottling to prevent CO2 loss. The bottling line is where everything shifts into high speed. Depending on the plant, the line can handle glass bottles, aluminum cans, or PET plastic bottles. Most modern facilities use stretch blow molding machines to convert PET preforms into full-sized bottles on site. This reduces shipping costs and allows for rapid size changes depending on demand. Each bottle or can first passes through a rinsing or sterilizing system. Bottles may be inverted and blasted with ionized air or washed with ozonated water. Cans are typically rinsed with sterilized water before entering the filler. Now, the carbonated Dr. Pepper is dispensed into containers using a rotary filling machine. This machine features multiple filling heads rotating on a carousel, with each head delivering the precise amount of liquid into each container. The filler operates under pressure to prevent foam and retain carbonation. As soon as the beverage is deposited, the bottle or can is sealed. PET bottles are capped using torque-controlled screw heads, while cans receive crimped-on aluminum lids in a high-speed seamer. Immediately after sealing, the containers pass under printers that apply batch codes, production dates, and expiration information. This coding is essential for traceability. If there's ever a recall or quality issue, the plant can trace every bottle back to the exact minute it was produced, the syrup batch used, and the operator on duty. Then comes packaging. Filled bottles are grouped into packs using shrink film, cardboard sleeves, or trays, depending on the final retail format. These packs are stacked by robotic arms onto pallets in precise configurations optimized for transport. The finished pallets are stretch wrapped, labeled with shipment data, and moved to the distribution warehouse. But before any pallet is cleared for shipment, the line's quality control team pulls samples from each production run. These are subjected to rigorous testing in the plant's on-site laboratory. Pressure tests confirm carbonation levels. Spectrophotometers check color uniformity. Sensory experts conduct taste evaluations to verify the blend is balanced. Microbial samples are incubated to ensure the product is sterile and safe. Meanwhile, automation software monitors the entire plant. From SCADA systems that track syrup bricks and carbonation pressures to IoT-enabled sensors that measure temperature drift in holding tanks, the entire operation is visible in real time to engineers and technicians. If a motor starts to overheat or a fill level goes out of spec, alerts are triggered immediately. Once quality is assured, the finished product is ready for shipping. Climate-controlled logistics routes transport Dr. Pepper to warehouses, distributors, and retail outlets. Some trucks are refrigerated, especially in hotter regions, to protect the product during transit. Whether it's a vending machine in a high school, a 12-pack in a grocery store, or a fountain soda in a fast food chain, Each container of Dr. Pepper must taste exactly the same. And that's only possible because every variable was controlled from start to finish. Beyond the factory, the Dr. Pepper production network also includes specialty manufacturing for fountain syrups, bag-in-box formats for restaurants, and concentrate shipments for international bottlers. These formats go through similar blending, filtration, and quality assurance processes, but are tailored for bulk use with different bricks and carbonation considerations. Every day, this system repeats across dozens of plants, with millions of cans and bottles produced and shipped with extraordinary consistency. Despite being made at different locations by different teams, every unit of Dr. Pepper shares the same flavor fingerprint: sweet, spicy, slightly fruity, with a creamy undertone and a signature bite. It's a beverage born in the 1880s, but produced today using some of the most advanced technologies in food manufacturing. From its mysterious blend of flavors to its perfectly balanced carbonation, Dr. Pepper represents a legacy of innovation, precision, and a dedication to quality that extends from syrup tank to store shelf. Sprite's story begins with water. While most people focus on Sprite's citrus flavor, the truth is that over 85% of what you're drinking is water. But not just any water. For Sprite to taste exactly the same in Singapore as it does in San Diego, bottling plants must purify their local water supply to a consistently neutral baseline, free from taste, color, odor, and minerals. The incoming municipal or well water is first screened through mechanical filters to remove suspended solids. It then moves through activated carbon filters that strip out chlorine, chloramines, and any volatile organic compounds. This ensures that the water has no off-putting flavors. Then it passes through either reverse osmosis membranes or demineralization columns, which remove dissolved salts and ions. Finally, a UV treatment or ozone injection kills any microorganisms. This ultra-purified water is held in stainless steel tanks, where it is monitored in real time for pH, conductivity, turbidity, and microbial counts. It must meet the exact specifications set by the Coca-Cola company before being allowed into any part of Sprite production. Only once it's passed all quality checkpoints can it be used to create the base for one of the world's most recognizable sodas. Parallel to the water treatment is the preparation of Sprite's proprietary flavor syrup. This part of the process is handled in a syrup blending room, often kept under positive air pressure and high sanitation standards to prevent contamination. The base concentrate used for Sprite, supplied by the Coca-Cola company, is delivered to the plant in sealed, food-safe drums or totes. This concentrate contains the citrus flavoring system, acidulants, and trace aromatic compounds that define Sprite's lemon-lime taste. Inside the blending tanks, equipped with high-torque agitators and recirculation loops, the concentrate is mixed with water and sweeteners to form the final syrup. The sweetener is usually high-fructose corn syrup in the United States, though in some countries, cane sugar is used instead. Citric acid and natural flavors help create that sharp, clean taste. The syrup is blended at specific Brix levels, a measure of sugar concentration, and is analyzed for consistency in labs adjacent to the blending floor. Once the Sprite syrup is blended and passes quality checks for color, taste, pH, and sugar content, it is sent to the proportioning system. This is where the final product begins to take shape. Inside stainless steel pipelines, the syrup is carefully metered and mixed with the purified water in precise ratios, generally around 1 part syrup to 5 parts water. This mixture is now the uncarbonated version of Sprite, flat, sweet, and citrusy, but still missing that all-important sparkle. Carbonation is added in the next step. The flat beverage mixture is chilled to near freezing, typically 33 to 36 degrees F, inside jacketed holding tanks. This is essential because cold water absorbs carbon dioxide much more effectively. A carbonator, one of the most critical pieces of equipment in the line, injects high-purity, food-grade CO2 into the chilled mix. The carbonation process is highly controlled. Bubble size, saturation level, and gas purity are all continuously monitored. Sprite generally carries between 2.7 to 3.0 volumes of CO2, giving it that signature effervescence and a sharp bite that enhances the citrus flavor. Once carbonated, the finished Sprite beverage is held under pressure in chilled, oxygen-free holding tanks. It is now ready for bottling, and this is where the production line hits its highest speed. The bottling line is a marvel of automation, capable of processing over 1,000 bottles or cans per minute, all synchronized to fill, cap, label, and inspect each unit with zero tolerance for error. First, the containers must be prepared. If PET bottles are used, they arrive as pre-forms, small, test tube-shaped blanks. These pre-forms are heated and stretch-blown into full-size bottles using high-pressure air inside precision molds. This process allows plants to manufacture bottles on-site, reducing shipping costs and allowing for quick changes in size or shape depending on market needs. The newly formed or delivered containers are then sent through a rinsing or sterilizing station. Bottles may be sprayed with ionized air, steam, or ozonated water to remove dust and kill microbes. Cans are similarly rinsed and then inverted before filling. The carbonated Sprite is then filled into each container using a rotary filling machine. The beverage must be filled under counter pressure to preserve carbonation and prevent foaming. Each filling nozzle is calibrated to deliver an exact volume, down to fractions of a milliliter. As soon as a bottle is filled, it immediately passes to the capping station. Caps and lids are fed in from hoppers and applied with high-speed capping heads that torque each PET bottle to specification. Aluminum cans are sealed with a crimping mechanism called a seamer, which attaches the lid using multiple rollers in rapid succession. The entire filling and capping sequence is enclosed within a clean, sterile zone to prevent contamination. With the product sealed, it's time for coding and inspection. Each unit is printed with a production code, batch number, and best before date using a high-speed inkjet or laser printer. Advanced camera systems immediately scan the bottles or cans for fill level, cap alignment, label position, and structural defects. Anything that doesn't meet specs is ejected from the line automatically. Now the finished bottles or cans are routed to the packaging area. Depending on the destination, they may be shrink-wrapped in multi-packs, inserted into cardboard carriers, or loaded into trays for larger retail formats. Robotic palletizers pick up these packs and stack them in precise layers, forming stable shipping units. Each pallet is stretch-wrapped, labeled with destination and production information, and scanned into the warehouse inventory system. Before these pallets leave the facility, the Sprite they contain has already been sampled for in-depth quality checks. Laboratory technicians pull random samples throughout each production run and test for bricks, pH, CO2 volumes, and sensory characteristics such as aroma, clarity, and taste consistency. These tests are performed hourly, sometimes more frequently, using calibrated instruments and trained panels. Additional microbiological testing ensures the beverage is free of spoilage organisms. Each batch must pass these hurdles before it is released for distribution. Some plants hold back every 10th or 20th pallet for additional hold and release protocols, where the beverage is stored under controlled conditions and monitored for early spoilage signs before shipment. From here, Sprite enters the logistics phase. Temperature-sensitive loading docks ensure that the product stays cool, especially in hot climates where carbonated beverages can suffer from premature expansion or loss of pressure. Climate-controlled trucks or standard dry vans, depending on the geography, transport the soda to distribution centers, retail warehouses, and vending machine operators. Behind the scenes, The entire operation is driven by powerful software, SCADA systems, programmable logic controllers, and cloud-connected ERP platforms. These monitor tank levels, syrup usage, CO2 flow rates, batch records, and even maintenance needs. Some lines are equipped with predictive analytics, using data to forecast failures before they occur, reducing downtime and ensuring maximum uptime. Every bottle and can of Sprite must conform to the same flavor fingerprint: balanced sweetness, bright citrus notes, clean finish, and a bracing level of fizz. Even with local water, different sweeteners, and various bottling partners worldwide, Coca-Cola's stringent standardization process ensures that no matter where you are, every Sprite you open tastes like it came from the same source. And yet, as science-driven as it is, the drink remains simple in experience. No caffeine, no color, just a bold, clear, citrus-flavored soda that delivers a refreshing hit with every gulp. A product of incredible precision, born in stainless steel tanks, shaped by sensors, robotics, and human craftsmanship, and enjoyed, often without a second thought, by millions. In the end, Sprite may be light and fizzy, but its production is anything but. It's the result of decades of process optimization, global logistics, sensory chemistry, and industrial control. And behind that cool green label lies one of the most tightly controlled and fascinating beverage production systems in the world. The production of Hershey's chocolate, from raw cocoa beans to the smooth, creamy bars found in stores across the globe, is a finely tuned industrial process that combines traditional chocolate-making techniques with large-scale factory automation. The journey begins with the sourcing of raw ingredients and extends through roasting, grinding, conching, tempering, molding, and packaging, all carefully orchestrated to deliver Hershey's signature taste and texture in every bar. The process starts at the very beginning of the supply chain, the harvesting and sourcing of cocoa beans. Hershey sources its beans primarily from West Africa, including countries like Côte d'Ivoire and Ghana, where cocoa trees grow in tropical climates. Once harvested, the beans are fermented under banana leaves or in wooden boxes for several days. This crucial step develops the deep chocolate flavor. After fermentation, the beans are sun-dried, sorted for quality, and bagged for export. Upon arrival in the US, Hershey's manufacturing facility inspects every shipment, checking for size, moisture content, and the absence of mold or pests. The beans are then conveyed into the cleaning and sorting machinery, where they pass through vibrating sieves, pneumatic suction tubes, and magnetic separators. This removes twigs, stones, dust, and any metallic particles. The cleaned beans are stored in large silos, kept dry and temperature controlled to preserve freshness. From here, they enter the roasting stage, which is one of the most important parts of flavor development. In the roasting stage, cocoa beans are fed into large rotating drums that heat them to between 120 and 150 degrees Celsius for about 30 minutes. The temperature and duration are carefully adjusted depending on the bean variety and flavor profile desired. During roasting, volatile acids are reduced and deep chocolate notes are intensified. The process also loosens the shells from the nibs, the edible inner part of the bean. As the roasted beans exit the drums, they move into the winnowing machine. The winnowing process uses high-speed fans and friction rollers to crack the roasted beans and separate the lighter shells from the heavier nibs. The result is a large volume of cocoa nibs, the pure form of chocolate, which are then transferred to grinding mills. These heavy-duty industrial grinders reduce the nibs into a thick, brown liquid called chocolate liquor or cocoa mass. Although the term liquor might sound alcoholic, it refers here to the liquefied state of cocoa solids suspended in cocoa butter due to the heat generated during grinding. Next, Hershey separates the chocolate liquor into cocoa butter and cocoa solids using hydraulic presses. The cocoa butter is a pale yellow fat that contributes to the creamy mouthfeel of chocolate, while the cocoa solids are rich in flavor. Hershey stores both components separately in stainless steel vats. For milk chocolate, which is the company's primary product, the recipe also calls for sugar, milk, lecithin, and flavoring ingredients like vanillin. One of Hershey's defining characteristics is its use of fresh milk, a distinguishing factor that sets it apart from European chocolatiers who often use powdered milk. In fact, Hershey operates its own dairy processing facilities in Pennsylvania. The milk is condensed and cooked with sugar to form a sweet, caramelized base that's blended with chocolate liquor and cocoa butter. This mixture is the beginning of Hershey's signature milk chocolate formula. This blend is then dried into chocolate crumb, a key intermediary unique to Hershey's process. The crumb is a dry, flaky mixture of milk solids, sugar, and chocolate liquor. It's stored in silos and later rehydrated with cocoa butter and emulsifiers during the refining stage. Creating crumb allows for a longer shelf life of the milk solids and helps develop the brand's distinctive, slightly tangy, malty flavor due to controlled milk fat breakdown during the crumb formation. Next comes refining, where the crumb and cocoa butter are combined and passed through a series of steel rollers. These rollers gradually reduce the particle size of sugar and cocoa to less than 30 microns. This fine reduction is critical for achieving the smooth mouthfeel of chocolate. If particles are too large, the texture becomes gritty. Too small, and it can feel pasty or dull on the tongue. The mixture exits this stage as a smooth, semi-fluid paste, ready for the next critical transformation, conching. In the conching process, the chocolate paste is agitated in large conche machines, steel troughs with granite or metal rollers that knead, heat, and aerate the chocolate continuously for up to 72 hours. This stage allows for further evaporation of unwanted volatile acids, the smoothing out of flavor edges, and the development of chocolate's rich, complex notes. The friction in conching also ensures the even distribution of cocoa butter, giving Hershey's chocolate its desirable melt-in-your-mouth quality. After conching, the chocolate is tempered. Tempering is the controlled crystallization of cocoa butter to ensure the chocolate sets with a glossy finish and satisfying snap. Hershey employs large-scale automated tempering units that carefully heat and cool the chocolate through a series of steps, bringing it down from around 45 degrees Celsius to 31 to 32 degrees Celsius for milk chocolate. This aligns the fat molecules into a stable crystalline structure, which gives the final bar its appealing texture and helps it resist bloom, where fat rises to the surface in white streaks. Once tempered, the liquid chocolate is piped into molds. The molding line consists of high-speed stations where molds are filled, vibrated to eliminate air bubbles, and chilled using cooled air or glycol-jacketed trays. For Hershey's iconic bars, molds are embossed with the brand's lettering and evenly segmented for snapping. The filled molds travel on a conveyor through a cooling tunnel that solidifies the chocolate completely within 8 to 12 minutes. Once cooled and hardened, the chocolate bars are demolded using a combination of vacuum systems and gentle mechanical actuators that pop them out without breakage. They move immediately into the packaging area, where a series of synchronized operations wrap, seal, label, and code each bar. Hershey's uses flow wrapping machinery that envelopes each bar in a foil and paper sleeve or film, depending on the product. The wrappers are printed with batch codes, best before dates, and product tracking identifiers. Every bar then undergoes quality control, which includes weight checks, X-ray scanning for foreign particles, and visual inspection by cameras that detect surface defects. Samples from each batch are taken to an on-site lab where texture, flavor, and microbiological safety are tested. If any irregularity is found, entire lots can be isolated thanks to the full traceability built into the production system. The packaged bars are then packed into cartons and stacked on pallets by robotic arms. The pallets are shrink-wrapped, barcoded, and sent to the distribution center. Hershey maintains temperature-controlled warehouses to ensure product stability, especially during summer months or shipments to warmer climates. Pallets are loaded into refrigerated or insulated trucks for distribution to stores across the country and abroad. What makes Hershey's chocolate truly unique isn't just the equipment or the ingredients, but the balance between automation and sensory control. While the machinery ensures consistency at massive volumes, sensory panels and chocolate experts continuously evaluate flavor, aroma, and texture to ensure every bar delivers the recognizable Hershey's profile. Even at the scale of hundreds of thousands of bars per day, this commitment to flavor accuracy and quality control is what maintains Hershey's reputation in the competitive world of confectionery. From cocoa bean to final bar, the industrial process behind Hershey's chocolate is a fascinating example of how tradition and technology merge. Every step, from roasting and grinding to conching and tempering, is carefully measured, controlled, and optimized. The result is a product that is not only nostalgic for many, but is also the outcome of over a century of engineering refinement and food science innovation. Cadbury's chocolate, with its unmistakably smooth texture and rich, creamy flavor, is one of the most beloved chocolate brands in the world. Its manufacturing process, while steeped in over a century of heritage, is executed today through a blend of tradition, advanced automation, and rigorous food science. At Cadbury's major production sites, such as the iconic Bournville factory in Birmingham, UK, every bar begins with careful ingredient sourcing and continues through precise steps involving milling, refining, conching, tempering, molding, and packaging. Across each stage, quality control, consistency, and signature taste are paramount. The first step in Cadbury's chocolate-making journey is the selection of raw ingredients. Cadbury's signature milk chocolate is made from a combination of full cream milk, sugar, cocoa butter, cocoa mass, and emulsifiers such as lecithin. Cadbury is known for using a relatively high percentage of milk solids compared to other mass-market chocolates, which contributes to its uniquely creamy flavor. For the UK and several international markets, Cadbury still uses fresh liquid milk rather than powdered or condensed forms. The milk is delivered daily to factories from nearby dairy farms, stored in chilled stainless steel silos, and constantly stirred to prevent separation. Meanwhile, cocoa beans, the fundamental ingredient in any chocolate, arrive at Cadbury's factories from West Africa, particularly Ghana, which provides a consistent, high-quality bean that is fermented and sun-dried prior to export. Upon arrival, these beans undergo detailed quality inspections before entering the factory system. They are cleaned thoroughly to remove foreign matter, dust, sticks, stones, or metal particles through a series of sieves, aspiration towers, and magnetic separators. Once clean, the beans are roasted. The roasting stage is one of the most vital steps for developing the chocolate's flavor. Cadbury uses hot air roasting techniques in rotating drum ovens or continuous flow systems, depending on the production volume. The temperature typically ranges from 120 to 150 degrees Celsius, and the roasting time can vary from 20 to 40 minutes. During roasting, the complex chemical reactions that form the Maillard compounds intensify the chocolate aroma and flavor, while also drying the beans to the ideal moisture level for further processing. After roasting, the beans are cooled and passed through winnowers, machines that crack them open and use air currents to separate the outer shells from the inner nibs. These cocoa nibs are rich in fat and flavor and form the base of both the cocoa mass and cocoa butter used in Cadbury products. The nibs are ground in heavy-duty mills to produce cocoa liquor, a thick, chocolatey paste made from pure nibs. Though liquid due to the heat generated during grinding, this liquor is made up of both cocoa solids and cocoa butter. At this point, the chocolate making process diverges depending on the final product. For Cadbury dairy milk and similar products, a crucial step involves combining the cocoa liquor with sugar and milk. Cadbury's defining feature is its use of fresh milk, which undergoes its own separate treatment. The milk is condensed with sugar in heated vacuum evaporators, producing a thick, rich liquid. This mixture is then blended with cocoa liquor and cocoa butter to create a homogeneous chocolate base. In traditional British-style chocolate making, as Cadbury does, this mixture is then dried into what is known as milk chocolate crumb. This dry crumb is unique to Cadbury and imparts a signature caramelized, malty undertone that distinguishes it from chocolates made with powdered milk or Swiss-style processing. The crumb is produced by drying the combined milk, sugar, and chocolate mixture in large drum dryers or vacuum drying systems, resulting in a sandy, dry granule that is easy to store and rehydrate in later stages. The crumb is stored in large silos until needed. When it's time to produce finished chocolate, it is remixed with additional cocoa butter, sometimes more cocoa liquor depending on the product, and emulsifiers like lecithin. This mixture is then passed through refining rollers, a series of 5 steel cylinders that reduce the particle size of the sugar and cocoa solids. The aim is to reach a uniform particle size of around 20 to 30 microns. This gives the chocolate a smooth texture without feeling gritty on the tongue. Particle size is verified using laser diffraction particle analysis systems to ensure consistency across every batch. Once refined, the chocolate enters the conching stage, named after the shell-like shape of early conching machines. This process involves mixing, shearing, and aerating the chocolate over several hours, anywhere from 4 to 24 hours, depending on the product. Conching removes volatile acids, unwanted moisture, and any rough flavor edges. Cadbury uses both traditional longitudinal conches and modern rotary conches, depending on the scale and specific chocolate formulation. During this time, the texture becomes silkier and the flavor deepens and rounds out. Following conching, the chocolate is transferred to the tempering line, one of the most delicate and technically controlled stages in chocolate manufacturing. Tempering involves carefully cooling and reheating the chocolate to encourage the formation of stable cocoa butter crystals, which give chocolate its shiny appearance and clean snap. Improper tempering can result in chocolate bloom, a whitish, dull coating caused by fat separation. Cadbury's tempering machines operate in a closed-loop system, cycling chocolate through a precisely controlled thermal curve. Advanced digital sensors monitor viscosity, temperature, and flow characteristics to ensure optimal temper structure. Once tempered, the chocolate is ready for molding. Cadbury's high-speed molding lines pour the liquid chocolate into molds made of polycarbonate or food-grade stainless steel, depending on the product. The molds pass over vibration plates to eliminate air bubbles and ensure even distribution. The filled molds then travel through a cooling tunnel that gradually reduces their temperature to solidify the chocolate without causing stress fractures. This ensures a uniform, glossy appearance and the correct snap when broken. Demolding is performed using vacuum lifters or gentle mechanical knockers, depending on the mold shape. For filled products like Cadbury cream eggs or caramel bars, the process includes an additional step. Shell molds are created by partially filling and spinning molds to create a cavity, which is then filled with the flavored fondant or caramel using precision depositor heads. These centers are allowed to partially set before a chocolate-based layer is applied, and the molds are fully sealed, then cooled and demolded just like solid bars. Once the chocolates are demolded, they move directly to the packaging lines. Here, automated machinery wraps individual bars in foil and branded sleeves or flow wraps them in film. The packaging materials are printed with batch codes, expiry dates, and traceability data. Optical scanners and X-ray systems perform real-time quality checks, looking for surface imperfections, air gaps, or foreign matter. Any product not meeting the strict standards is ejected from the line automatically. The wrapped bars are then grouped into cartons or multi-packs, which are robotically packed into shipping cases. These cases are barcoded, palletized by robotic arms, and shrink-wrapped for shipping. Pallets are stored in temperature-controlled distribution centers until they are shipped out to retailers. The entire inventory system is managed using enterprise-grade software that tracks each chocolate bar from production to warehouse to store shelf. What distinguishes Cadbury's industrial chocolate production from others isn't just its recipe, but its integration of craftsmanship and automation. Despite being a global brand, producing millions of bars per week, Cadbury maintains tight control over flavor, texture, and appearance through every stage, from the exact ratio of milk solids to the particle size in refining and the thermal curves of tempering. Every sensor, every conveyor, and every batch record plays a part in delivering a final product that's as familiar as it is meticulously engineered. Even sustainability is built into the process. Cadbury's factories are gradually moving toward carbon neutrality, with newer systems recovering heat from roasting for use in conching, and solar panels offsetting daytime energy use. Additionally, cocoa is increasingly sourced through the Cocoa Life program, which promotes fair trade, farm productivity, and community development in West Africa. In the end, every Cadbury Dairy Milk bar is a result of over a century of refinement, rooted in British chocolate-making tradition, but carried out in some of the most sophisticated food production environments in the world. From fresh milk and raw cocoa to the purple-wrapped bar, every step reflects a balance of nostalgia and precision, heritage and innovation. Mars chocolate bars, instantly recognizable by their dark chocolate coating, nougat core, and caramel layer, are manufactured through one of the most highly refined industrial processes in the global confectionery world. While the experience of biting into a Mars bar feels simple and indulgent, the behind-the-scenes production is anything but. It requires precision control of temperatures, flow rates, ingredient ratios, and mechanical handling, executed across multiple synchronized systems in high-speed, high-volume manufacturing plants. The entire process, from raw ingredient reception to molded bars in wrapped form, is designed for repeatability, safety, and sensory consistency, ensuring every Mars bar tastes identical to the last, whether it's made in the UK, the US, or elsewhere. It all begins with sourcing the core components: cocoa, sugar, milk, glucose syrup, and fats. Mars procures its cocoa through long-term supply contracts with farms across West Africa, where cocoa beans are fermented and dried on site before being shipped to processing facilities. Sugar is sourced from sugar beets or cane, depending on the regional plant. The milk component often comes in the form of milk powder or condensed milk, chosen for stability and easier integration into industrial formulations. Mars also uses specialty fats, vegetable oils, and cocoa butter blends for different parts of the bar to achieve specific textures and melting properties. Each of these ingredients is subjected to stringent quality control upon arrival. Cocoa powder is tested for fat content, microbial load, and flavor integrity. Milk powder is checked for protein and moisture levels. Sugars are screened for crystal size and cleanliness. Once cleared, they are transferred to bulk storage systems that feed directly into the production lines through enclosed, pressurized delivery tubes to minimize contamination. The first component to be produced on the line is the nougat base, which forms the soft but chewy core of a Mars bar. Nougat for Mars bars isn't the traditional egg white variety seen in artisanal confectionery, but a carefully engineered formula based on a whipped blend of sugar, glucose syrup, hydrolyzed soy protein, and milk powder. The dry and liquid ingredients are first mixed in large batch tanks equipped with high shear mixers. The mixture is heated to approximately 120 degrees Celsius to dissolve all solids and activate syrup structure, then cooled rapidly as it enters the aeration system. Aeration is critical. The hot syrup is whipped with nitrogen gas, chosen over air or CO2 because it's inert and maintains longer shelf stability. This whipping happens in high-capacity continuous mixers equipped with rotor-stator assemblies that shear and expand the mass into a light, foamy structure. The density is controlled down to the gram per cubic centimeter using inline flow meters and laser sensors. The freshly aerated nougat is extruded onto a cooling belt made of food-grade stainless steel or polyethylene-coated fabric. The belt runs beneath a cooling tunnel where chilled air brings the nougat's temperature down to a manageable level for further layering. At this stage, it appears as an endless beige ribbon, roughly the width and height of a Mars bar. Next comes the caramel layer, which is produced in parallel and deposited directly onto the top surface of the nougat ribbon. Caramel in Mars bars is made from a cooked mixture of glucose syrup, sugar, dairy solids, and fats, brought to a high boil under vacuum to reach the right viscosity and prevent crystallization. Caramel cookers, jacketed stainless steel kettles fitted with vacuum systems, ensure that the water content is carefully reduced without burning the sugars or degrading the milk proteins. Once cooked, the caramel is pumped into a spread depositor, a mechanism that lays down a smooth, even layer of caramel over the moving nougat sheet. The temperature of the caramel during application is closely monitored, usually around 40 to 45 degrees Celsius, to maintain spreadability without melting the nougat underneath. As the composite sheet of nougat and caramel moves along the line, it enters a laminar cooling tunnel, where chilled air slowly brings both layers down to cutting temperature. This ensures that the final bar will maintain its shape during slicing. After exiting the cooling tunnel, the layered slab is conveyed to a guillotine cutter, an automated, high-speed mechanical blade that slices the continuous sheet into individual bar-sized pieces. The cutter is synchronized with the speed of the conveyor, allowing it to produce thousands of consistent cuts per hour without crushing or dragging the layers. Optical sensors track the integrity and alignment of each cut, automatically rejecting any malformed pieces before they move to the next phase. The sliced centers are now ready for enrobing in chocolate. Each nougat caramel piece is placed onto the in-feed conveyor of a high-speed chocolate enrober. This machine pumps liquid chocolate, produced from a blend of cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, over the bar in a curtain-like flow. The bottoms are coated first by passing over a shallow chocolate bath. Then the rest is coated from the top and sides via falling curtains of tempered chocolate. The chocolate used in Mars bars is carefully tempered beforehand. Tempering is the process of heating, cooling, and reheating chocolate to create a uniform fat crystal structure, giving the coating its shine, firmness, and resistance to bloom. Mars uses fully automated tempering units that precisely control chocolate temperature to within fractions of a degree, cycling through heating coils and chilled plates in sequence before delivery to the enrober. As each piece exits the enrober, it passes over a vibration plate that shakes off excess chocolate and ensures even coverage. Some lines use air knives, streams of compressed air directed at specific angles, to remove chocolate buildup from the sides or base of the bar. The freshly coated bars then enter a cooling tunnel that runs for 15 to 20 meters, gradually reducing their temperature in controlled stages to prevent cracking or moisture condensation. These tunnels use chilled, dehumidified air at around 8 to 12 degrees Celsius. Once the chocolate has fully set, the bars proceed to the wrapping line. Here, high-speed flow wrapping machines encase each bar in metallized polypropylene film, heat sealing both ends and the back. Wrapping machines include inline printers that apply the best before date, batch number, and factory code directly onto the film. Optical scanners check each wrapper for print clarity, alignment, and seal integrity. Any bar with misaligned film or poor sealing is ejected from the line by pneumatic arms into a separate rework bin. Wrapped bars are counted and grouped into cartons, which are then sealed, labeled, and moved to robotic palletizing systems. Robots arrange cartons in predefined patterns onto pallets based on flavor, size, and shipping destination. Each pallet is barcoded and logged into Mars' ERP system for real-time traceability. Pallets are stored in climate-controlled warehouses maintained at 18 to 20 degrees Celsius and under 50% relative humidity to preserve the chocolate's shelf life and prevent bloom or fat migration. The entire production line is monitored via SCADA systems, software platforms that oversee machine parameters, product flow, and quality metrics in real time. Operators at control stations can view temperature logs, flow rates, equipment performance, and reject rates. If a sensor detects even a slight deviation, like a variation in caramel viscosity or enrobing temperature, alerts are issued and adjustments are made immediately to avoid wasting product or compromising quality. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat, while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conches are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable Form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs, which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance, particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names, holiday messages, or even national flag motifs. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough-making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal, high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance. check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and queued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel's structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, The dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data, embedded in barcodes or RFID tags, about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars' global standardization team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat.